Okay, I'll.
Yes, now the next speaker is Danylo Yakymenko from Institute of Mathematics in Kyiv. Algebraic structures for quantum algorithms and protocols. Please, Danylo, 25 minutes.
Yes, greetings everyone. Thank you for introduction. I will talk about some of our research of mine and my colleagues of researchers, my colleagues from the Institute of Mathematics. Our Institute of Mathematics is a part of National Academy of Sciences of National Academy of Sciences of Ukraine. It was founded in 1934, and now it has 11 departments and with some various fields of research in mathematics. Our institute mostly does some research, but we also have programs for postgraduate students. I'm represent today our department. It's the Department of Functional Analysis, and our current head is Professor Vasily Ostrovsky. Okay, and what our research topics? There is some branch of our research which can be called algebraic problems of functional analysis. What is included in this branch? It's a representation theory of different algebras and operator relations in Hilbert and linear spaces. For example, some theory of C-star algebras or just algebras with involution, and different. We study different examples, some and for example, some quadratic relations between operators. We just find and classify its representations. There, for example, there is research about some deformations of well-known classical algebras, for example, deformations of Kunz algebras, and investigation of problems related to the representation theory of such algebras. Another topic is we study and classify systems of subspaces in Hilbert and Banach spaces. So maybe some of you know there is a known paper by Halmos called two subspaces, and it's about classification of just two subspaces in the Hilbert space. So there is a and we can the theory of classification. So it is about how two subspaces are related to each other and how can we classify them. But we can try to extend this theory on most system, on a system of bigger number of spaces, but in general it's actually a hard problem. And so what we do is we study system of subspaces that are related to some that have some additional relations between the subspaces, and which are motivated by some algebraic relations. And no, I will talk a little bit more about this later. And we also study. There is also research about. We both study subspaces in finite dimensional and also in infinite dimensional spaces, and then we study some questions about, for example, when the sum of closed subspace is closed. There are research about this, for example, too. There is also research connected to some spectral theory of operators in Hilbert spacers, for example, and there is a research that can be classified as a research in a frame theory. I will also touch this further, and there is, of course, another branch of topics that we study in our department. It's mostly a continuation of the old school that was started by academician Yuri Berezanski. And there is some study of inverse scattering problems, soliton theory, and many other questions of, let's say, classical functional analysis. But this branch is related to actually quantum modern. It is related to modern quantum problems, I would say. Okay. And what are those modern quantum problems? There is various kinds of quantum algorithms and protocols that are connected to this novel quantum, let's say, research topics that use quantum computations. So, for example, there is a question about quantum tomography, including and entanglement detection, right? So, in quantum tomography, we know that we have a state, and we know, for example, we can know some properties of this state, but we don't know exactly what the state exactly, and we need to construct a protocol, a protocol of tomography, how to measure the unknown state in the most efficient way to actually find the answer about it. Okay, and quantum entanglement detection, if it's a algorithms when we have a state and we want to find out if a bipartite state, is it entangled or separable, which is and these questions actually, the question about entanglement detection is actually very hard. So there is no nice efficient solutions, but there are some different methods, including Perez PPT partial transpose criterion and other various algorithms. Another topic is a construction of efficient quantum circuits is for it's specifically interesting for quantum computers of common common structure where we have just a number of qubits and we can operate on the fixed number of qubits. There is also quantum error correction codes and the topic another topic which I also called modern quantum science is a quantum cryptography, and specifically it's K distribution. There are, of course, many other quantum research like quantum simulations, quantum machine learning, and other research. But I mostly I will concern about these research branches. Okay. Now, I want to talk about what is called PUVA. It's most of you probably know it's a PUVM. It's a positive operator valued measure. What is it? It is just a set of positive semi-definition operators, and here I call a finite dimensional space. So, but it can be also defined by in an infinite dimensional Hilbert space too, and it is a measure if the sum of these operators is just identity on the Hilbert space. Now, this is actually a foundational algebraic structure because it is the most general way to model measurement in quantum mechanics. Whenever we have some measurement, then there is always a related PUVM, and whenever we have a state and we apply the measurement corresponding measurement of the state rho, then the probability of the result I is just given by this formula. And the PUVM in most situations on a practice or even in theory, mostly most people interested in PUVMs such that those operators they are actually projectors, maybe up to a scalar, right? So, for example, there is just a PVM, just projection value measures, and for example, Wynayment measurement, where we just have a basis, a measurement that we can construct from just an orthogonal basis, right? Okay, and and what we done in our department is that we started to investigate actually this kind of problems that are related to this algebraic structure. For example, there is a paper titled "On the Sum of Projections," and in this paper, it was studied the set of all possible numbers lambda, such that the sum of projectors is this multiple of identity, right? So there is a corresponding POV, and it was the set was completely described, and it was used. And in this box, there was developed different methods. How can we investigate such systems? and these methods were generalized in the next work in our department. So, for example, we can put coefficients. So here you can see that coefficients are the same, but we can consider different coefficients and investigate similar problems. Of course, the most interesting problem is to classify all possible POVMs, how they can be constructed. But this is actually a very hard problem. So it can be, if the number of elements in POVM is 4 or less, then there is a full classification of POVM of this type. But whenever n is bigger than 4, then this problem becomes very hard. And so what we do, what we've done in our research is that we we consider some additional relations between the corresponding projectors, and then we study and classify those POVMs. Okay. I want specifically I want to talk about a very interesting and foundational type of POVM. It's what is called SIG POVM. It's symmetric, which means symmetric informationally complete POVM. It is a POVM where every operator is just a projector on a single state, on a single vector, and there is a d squared of them, and the angle between any two different vectors or states is actually constant. Now it turns out that this symmetry is actually very, very useful, because this POVM it is like it is optimal from it becomes optimal from multiple views. And for example, there is the whole interpretation of quantum mechanics called cubism, quantum-based Bayesianism, where SIG POVMs is considered as the fundamental measurement. Now, but the problem is we know how to construct SIG POVM in some small dimensions, but we actually don't know. So we can prove that there exists always, that there exists in every dimension. It's a still open problem, and it's more than for 20 years. Many people in the world know this problem and try to prove it. And there is also a related structure. It is what is called MUBs. It's a mutually unbiased basis. MUB is just a pair of orthonormal bases that where the angle between vectors from different bases is constant. And whenever D is a prime power, then D plus 1 pairwise mutually unbiased bases, they always exist. We can construct them, right? For example, for a qubit, we have these three bases, which are pairwise mutually orthogonal. But there is another interesting open question in quantum information. What is actually the maximal number of MUBs in general dimension there? and it can be more than d+1, but we don't know what the answer. We don't know even if for d equals 6, we know that there are 3 mutually unbiased bases, but we don't know if 7 is possible or not, right? And I want to say that MABs are also very useful measurements. They are used in quantum cryptography, or just I believe you could hear yesterday how people were saying how they use MABs in their research. And those structures actually can be generalized, and there is what is called quantum T designs. It is a set of states that it is a such set of states that if we take an average of tensor powers of projectors, tensor powers to the order T, and then it is essentially an average of all possible. That's without pi. It's just average of all possible projectors. Okay, and there is a. It's also useful. It's also useful for different kind of algorithms. And another, there is a related. To quantum just T design, there is a related notion of unitary T design, since when it's just a set of unitaries, where it is a set of unitary matrices of D times D, such that satisfies this formula. And the unitary T design is also useful, for example, in some quantum benchmarkings, or for example, we can there are so-called unitary bases, and it is known that unitary bases are one designs, and unitary bases are also useful in many algorithms. For example, in quantum teleportation, you can generalize an ordinary schema of quantum teleportation to use just unitary basis in some d-dimensional space, and use and implement teleportation using those generalized unitary bases. Okay, so, and there is also another problems that we study in our departments. For example, there is a questions about the composition of unitaries. You know that it is essentially when we construct a quantum circuit, we try to decompose a unitary into some other unitaries in some specific manner, in some efficient manner. There is a research that's related to these problems, but not directly related, but there are some you can find some similarities. Now, for example, there is a result. Well, this is a result about infinite dimensional Hilbert spaces. So it's a theorem that states any unitary is actually a product of 4 reflections. Right? Reflections are just a unitary with that the square root of identity, and this can be actually generalized, and we can show that any unitary is a product of just 3 roots of unitary of such orders that satisfy this relation. Now I didn't show on the slides, but whenever we have another inequality, then we can there is actually interesting relations between roots of unity of such orders.
Danylo, sorry, it's time.
Yes. Okay. A couple of words, if you may. There is also research about the compositions of operators. When we try to express a Hermitian operator as a sum of projectors. So there is actually, of course, there is a spectral theorem that says how you can decompose Hermitian operator, but it is interesting it is also interesting to decompose the matrices into some linear combination of projectors. Okay, and there is a research of this type. Okay, this is all what I wanted to say. Okay, thank you for
almost in time. Thank you very much.
Attention.
Time for one quick question. Andrei Semenov, please.
Yeah, Danylo, thank you for your talk. Just one very short question. Your result about decomposition of unitary operator.
Yes.
Yeah, could you please give one quick example how it can be useful for quantum computing?
Well, I can say right about. I can say can't say about exactly this theorem, but there is a when we look at this, when we take three roots of unity of orders with the where this where they are small enough, right? Then there are relations between them, and those relations, I think, well, actually, I'm thinking about how those relations between those roots can be used to construct some error correction codes, and for example. So we can. There is a matrices that satisfies certain specific relations between them, and there is a, and it is what in general it is what's used in quantum computing. For example, in stabilizer codes, we take a group of we take a Pauli group, generalized Pauli group, right? And there are relations between unitaries. There is also a Clifford group of unitaries, and there are also relations between them, and they are all used. They all used in quantum computing, mostly in error correction. They're used, but there are also
for error correction very useful results. Okay, thank you very much.
Thank you for the question, Danylo. Thank you so much for the talk. There's the question in the chat. However, we'd better go to the next speaker so that to stay more or less on the schedule. Please continue discussion via chat or email. The next speaker is Filip Maciejewski from the Center for Theoretical Physics in Poland.